In this Lab 3, we were given relevant data, a star's mass, a fitting time step, and the position of an object it's orbiting around, in this case, a black hole. From this data, a CSV file containing the star's path in vectors around the black hole, and our existing knowledge of gravitational pull and momentum, we were able to find the black hole's unknown mass. This is the code I used to find the unknown data. I input the mass and the time step, set to be the length of a day in seconds, an Earth day at least. I changed the equations within the calculation loop to reflect the values in the momentum principle equations. Momentum, shown here as P initial and P final, are calculated by the star's mass multiplied by their respective velocities, final and initial. The deltas are found by subtracting final values from initial. We are also asked to discuss how Fnet perpendicular, Fnet parallel, and Fnet differ from delta P over delta T perpendicular, delta P over delta T parallel, and delta P over delta T. In this case, delta P over delta T simply gives the change in momentum divided by the change in time, which is just the change in momentum over the change in seconds. Fnet is equal to dp dt because the gravity force found this way is the only force acting upon it. The gravitational pull of the black hole, that is. The parallel and perpendicular values for Fnet are also calculated. First, the unit vector p hat is found by dividing the initial momentum vector by its magnitude to find the direction of momentum. Then the magnitude of delta p over delta t is found and multiplied by this unit vector to give the momentum in the direction of velocity. This is also equal to Fnet parallel because there is only one force acting upon the star. Because we do not have a relevant radius to use, dp dt perpendicular must be found using already calculated information instead of the mv squared over r equation. The parallel component is subtracted from the total force, yielding the perpendicular component. The aeroscale was changed to better suit this ellipse. Finally, the gravitational constant was input, along with an equation to find the unknown radius of the orbit by subtracting the star's position at that time minus the given position of the black hole at the center of the ellipse. To solve for the unknown mass, the gravitational equation shown here was rearranged to solve for the mass of the black hole while inputting the given information. When run, the orbit looks like this. Originally, to get the most accurate mass, I put a print statement at the end of the calculation loop and took an average of all the values it gave. Because these all differed slightly due to the star's elliptical motion instead of circular, an average was the best result. Here are those values. There are about 1,000 of them, and they only differ by a small amount. I also used Excel to find the average, the standard deviation, and the coefficient of variation of this data shown here. Another question asked what would happen if the black hole was removed and substituted for one of a different mass. However, the star's orbit remained unchanged and was still only affected by the black hole's gravitational pull. Could I tell the difference and find this new object's mass? Well, if the star's exact orbit was unchanged, then the mass of the new object would have to be very similar to the one calculated in this experiment. If it only differed slightly, and we had the data and the CSV file of that information, it could be input into this code and treated just the same way.